Assalamualaikum warahmatullahi ta'ala wabarakatuh. We from the group 4, today we gonna present about our project, which is aircraft engine bracket analysis.
This group consists of 3 students, which is me, NUQMAN MAHATHIR bin ELHAM, adik FARHAN bin Muhammad ROSLAN, and IZZUDDin bin AMRAN. Our main focus is on redesigning an aircraft engine bracket to make it lighter, more environmentally friendly, and cost effective. Although the bracket does not operate during flight, it must withstand high mechanical loads during engine servicing. The original bracket, made from titanium alloy, is strong but expensive and energy intensive to produce. It is replaced with magnesium alloy, which is lighter and more sustainable. Our aim on this project is to reduce the bracket mass to under 0.8 kg, limit deformation to under 0.35 mm, and maintain a factor of safety (FOS) between 1.2 and 3.0. To evaluate the design, 3 analyses using NCCAE software were performed, which is number 1 is linear static analysis to test strength under load. Number 2 is thermal stress analysis to assess performance under temperature change, and 3 free vibration analysis to ensure safety.
So the objective is we need to redesign the aircraft engine bracket using more sustainable materials. So we use a magnesium alloy. Secondly, we need to meet the performance target. Thirdly, we need to analyze structural behaviors such as total deformation, maximum equivalent von Mises stress, and also factor of safety. And finally, we need to design to support SDG 12, which is promote sustainable design and responsible material use. So me as a student 1, which is adik FARHAN bin Muhammad ROSLAN, will perform the linear static analysis. So the purpose of this analysis is we need to test the design under 16,500 Newton of load, which is we apply for the 3 design that we create. Secondly, we need to check the maximum stress, which is equivalent von Mises stress. Secondly, the total deformation, and also and finally the factor of safety, which is FOS. The criteria that we need to achieve is maximum deformation of below or same as 0.35 mm. The FOS is in between 1.2 to 3.0, and the mass is below 0.8 kg. So as you can see in this slide, we create the 3 design, which is follow the specification that given to us. So this is design 1, design 2, and also design 3. So after performing the linear static analysis for the 3 design, only the design 1 that achieve the target that we need. So as a result, you can see at the slide, the design 1 achieve 0.71217 kg, which is below 0.8, and the FOS is we need to divide it tensile yield strength. We need to divide it by 2 maximum equivalent von Mises stress, which is 193 megapascal divided by 156.71 megapascal, and we get 1.2295 as a FOS, which is in range between 1.2 and 3.0. And lastly, the deflection or total deformation. So for the design 1, we get 0.24627 mm, which is below 0.35 mm. So this is a color contour plot for total deformation at design 1, maximum equivalent von Mises stress for design 1, and the next slide, which is factor of safety for design 1. We also show you the mass value, which is 0.71217 kg, which is below the 0.8 target. So the achieved result from the design 1, we need to compare the percentage with targeted value. So as you can see, the mass percentage with the design 1 and the targeted value is 10.68%. Secondly, the FOS difference, which is 2.46%, and the deflection percentage is 29.64%.
So Assalamualaikum and good morning everyone. So I will presenting about this thermal stress analysis. So the purpose of thermal stress analysis is to stimulate bracket performance from 25 degrees Celsius to 100 Celsius. So the second purpose is to identify the thermal stress effect. Okay, and the initial setup is to the bracket is fixed at the mounting hole and subjected to 16,500 Newton of load, and then the thermal condition is applied uniformly. The different temperature is 75 Celsius. So this is the result for thermal stress analysis. So the maximum total deformation is 0.4282, and the equivalent stress is 876.57. So the minimum factor of safety FOS is maximum is 15. Okay. Okay, so this slide show that comparison between with and without thermal change. So for the von Mises stress, without thermal change, the value is 156.97 MPa, and with thermal change is 876.57 MPa. So the summary is it increased by 448%. So for the total deformation is without thermal change is 0.24627 mm, and with thermal change is 0.42482 mm. It increased by 72%. So the factor of safety without thermal change is 1.2295, and with thermal change is 0.22018. So the value decreased drastically around 82%.
I'm going to explain about free vibration analysis. Our main purpose is to calculate the natural frequencies and mode shapes of the bracket to avoid resonance with the engine excitation frequency of 275.8 Hz. As you can see, this is the color contour plot result for 5 modes in free vibration analysis. Number 1 is simple bending. The max value of total deformation is 105.52 mm with the frequency of 4023.7 Hz. So the structure was considered to be safe from the resonance. Number 2 is transverse bending. The max value of total deformation recorded is 25.928 mm with the frequency of 5451.2 Hz. The structure was considered also safe from the resonance. Number 3, bending of middle span. This max value of total deformation recorded is 78.499 mm with the frequency of 7223.7 Hz. This structure also was considered safe from resonance. Number 4 is twisting. The max value of total deformation is 186.3 mm with the frequency of 8792.6 Hz. So this structure was considered to be safe from the resonance. And lastly is bending at quarter span. The max value of total deformation is 68.163 mm with the frequency of 12,096 Hz. This structure also was considered to be safe from the resonance. The analysis shows that the bracket has very high natural frequencies, with the first mode starting at 4023.7 Hz. This frequency represents how the bracket naturally vibrates when it's disturbed. Each mode has a unique deformation shape, and among them, mode 4 stands out. It caused the most noticeable twisting in the structure.
So for structural improvement recommendation, for linear static analysis, we need to optimize more on geometry. Secondly, we need to utilize topology optimization tool. And thirdly, reinforcement or ribbing addition. For thermal stress analysis, firstly, material substitution for high temperature environment. Secondly, supply expansion gap or flexible support. And thirdly, use thermal coating or insulation. And lastly, for free vibration analysis, we need to reduce undesirable vibration through damping characteristic. Secondly, we need to improve mass distribution. And lastly, we need to increase thickness of most heavily deforming region in mode shape.
So for the conclusion, the linear static analysis confirmed that the bracket is lightweight, stiff and structurally safe under 16,500 Newton static load. but the thermal stress analysis shows the bracket is vulnerable to high temperature collision, exceeding the deformation and stress limit with a critically low factor of safety. So the free vibration analysis confirm all natural frequencies are above the engine's excitation frequency 275.8 Hz, eliminating the resonance freeze. So thank you.